Hello everyone, welcome back to the course on system programming, your favorite course of lectures, on which we are looking at various system programming related stuff. And today's lecture is about files, file systems, file devices, virtual file system, how it's working in the kernel, in the hardware, in the user space, specifics of page cache, speeds of different devices, and everything that might be related to that, at least from my experience. The plan of today's lecture is the following. We first look at what file systems are, their purpose. We look then at storage devices on which file systems usually get mapped, like HDD and SSD. We will see how they are working, what are pros and cons of every trade-offs. Then we will look at file system structure in general, how it is structured. Then we look at some specific file systems such as FAT and ext2. Then we look at how virtual file system is working in the kernel and what it even is, virtual file system. Then we look at IO scheduler, page cache, and then I will give you the new homework to do. Previously we have looked at how a process can work with file descriptors, read something into its memory, build pipes, and it turned out that file descriptors are created for each open. They can be reference counted, but a file descriptor is not just a number. In the kernel we saw that this number that we have in user space, this int fd, it's actually an index in an array of file descriptors, which in the kernel we show as a struct fd table. You can see it has capacity max fds and it's just an array of pointers. And the user space file descriptors are simply indexes in this array. We also show that those file descriptors in user space being numbers, they point at this eventually struct file object, which internally points at a strange structure inode. And I promised you last time that we will look into that eventually, and this is the time today to look into what is inode, what is behind this virtual object of struct file. In this lecture we will learn what is hidden inside struct inode, how a file system works, how it's organized, how the kernel manages IO operations, and what the kernel does to speed the file access up. So on our picture from the first lecture, we're going to dive into this section of file systems. Why do we even need file systems at all, and devices for them to work on? Why can't we just have a pile of files unstructured on some sort of random device? Instead we have HDDs, SSDs, flash drives, and all of them can have different file systems for different purposes. Well, file storage separately from the main memory we need in order to store something not just in the main memory. Why don't we store everything in main memory? Because as we saw in the previous lectures, it's almost always DRAM, which is volatile, which means it does not save the state of its capacitors or transistors when the power is off, so it will lose all the values that are stored there. All the bits will be like messed up. So we need persistent storage, which usually is HDDs and SSDs. There is also NVM, non-volatile memory, which can be used as RAM, but it's quite expensive and it cannot be too big. Also, main memory is small in size. Sometimes even at runtime, we just might be unable to store something completely in main memory. Even if it is some temporary data, we still might have to store it on disk temporarily, because it simply doesn't fit into RAM. For example, imagine a use case when we need to perform merge sort of some large array of whatever objects and they do not fit into main memory. Can be like multiple files, each being tens of gigabytes, hundreds of gigabytes, or like hundreds of files, each of which is tens of gigabytes. This, in theory, can easily be possible in some high-load systems, and we need to sort it into a new sorted file. You cannot just load it all into memory, call qsort, and then write it into a new file. It just doesn't fit into memory. So then you need to apply certain algorithms which will help you with that, like merge sort, which will sort the files in parts, and then you can write the final sorted data in parts, like reading those pre-sorted separate files one by one item by one item, and then you choose the next one and the next one. So the typical merge sort algorithm. This way you can sort pretty much quite a lot of data, even if it doesn't fit in total into your main memory size. And this might even sound a little bit artificial, I would say, this merge sort thing. But I can tell you it's quite a real task. And it's not even super extra high load, because we, for instance, in Interan tool database, there is used memory structure called LSM3, log structured merge tree. And basically what it is, it's multiple layers of files. On each layer there is a file. Each file is just sorted array of keys. And when data is being written into this LSM3, this data firstly piles up in the main memory, and then it gets dumped onto the disk. And then on the disk you have eventually some number of files, each having sorted keys. And after a while, you want to reduce the size, because some of those files will have duplicate keys. Like if one key gets updated multiple times and gets written into multiple files, you might want to compact those many files into one. And guess what? This stuff you will do with a merge sort. So this is a relatively real task, especially in databases, easily imaginable. On this slide, I show some prices for different types of memory to see another difference between main memory and persistent disk memory. The prices might be a little bit outdated. At the moment of recording this video, we're at the point where RAM costs more than gold, but still the relative difference between RAM and HD and SSDs, I think, is going to remain roughly the same. So don't pay attention to the absolute prices. They will probably stabilize anyway at some point. So when I last checked it 3 years ago, just to see what is how much more expensive than other stuff, I saw that for RAM you will pay for 1 gigabyte approximately €2.81. If you buy an HDD 3 years ago, from the moment of recording this, 1 gigabyte of HDD was 3 cents. And it's 94 times cheaper. If you buy an SSD, 1 gigabyte will be 6 cents. It's 46 times cheaper than RAM. So even right now, prices probably for all of those three types of devices went quite a lot up. But anyway, probably the relative difference remains roughly the same. And this means that when you can afford to buy an HDD or SSD, because you don't need such strong guarantees of speed of access, then you better buy them, because then you will save money. What is commonly meant as a file system? There are three versions of definitions, I would say. The first definition would be that file system is just all the files that you have on the computer, starting with the root folder. Or in case of Windows, starting with the disk name folder. The second definition we could say is that file system is a storage format, according to which the data is organized in a certain way, and represented by some structures with description of what is stored by which offset, which bytes mean which file, which bytes mean which folder, which files belong to which folder, and so on. All this stuff you need to encode somehow, right? Into a sequence of bytes, which you would store on disk. And this structure, how to encode your files and folders into bytes, into stable bytes, not dependent on any stuff like virtual memory. This is we could also call a file system. And also sometimes as a file system mean a partition. So when you partition your disk into multiple segments, on one you can store like one operating system, on another operating system, and have different file systems. Sometimes this partition thing is also called file system, although probably the most correct definition would be the second one. It's like a protocol, the format in which you decide to encode your files and folders, so that any computer later can also decode it if it follows the same format. Like a network protocol, but for disk. What tasks should the file system solve? Like the main job of the file system. What does the kernel expect from it, user space expect from it? First, the namespace by which files are accessed. So the file system should provide you to access files and folders by names, or just files. The file system might even not have folders. Nothing in the definition of file system forces you to have folders. It's just a convenient thing that most file systems have, but they don't have to have it. Storage format, yeah, file system should describe how to encode files and folders. I don't mean encrypt, to be clear. I mean literally encode. How to save name of a folder, for example, on disk. You would probably, to be able to decode it back, write some specific header like name consists of four bytes specifying name, length of the name, and then the rest of the bytes is literally the characters of the name. I mean, low-level stuff like this. And also, a file system should provide a certain API, like what is possible with this file system, how you can open and close the files, does it support credentials, access rights, ownership of files and folders, what types of files and folders it supports, because there are different types. For instance, on Linux, you would probably expect that file system should support file type like a Unix socket, while on some other file system it might be not possible. And part of this API, important part, would be protection, so the file system should define some sort of restriction of access for different users, so they could not mess up each other's files. But I think this is kind of optional thing anyway, for a general file system. And last but not least, of course, implementation. Implementations can be many, as long as the definition of the format, of the naming, of all these APIs is standardized in some way. There can be many implementations, like for a file system ext, there might be implementation inside Linux kernel and inside Windows kernel. This would probably be different implementations, but doing the same, providing the same API to their kernels. It's important to realize that file system is actually software and documentation and standards. It's not hardware. On a disk, you don't even need to have any file system at all. File system is just something that we need to perform high-level operations on a certain array of bytes. This array of bytes can be anything. It can be a disk, it can be RAM. You can allocate some memory in RAM and then say that those several pages of RAM will store this file system. Easily, this is possible. Because file system can actually just exist on any blob of bytes. It can be hardware bytes, it can, like from a disk, it can be bytes from RAM. Doesn't matter for the file system itself. It only matters for us for the guarantees. Like if you create a file system on top of some virtual memory, like in your user space process, then you will expect that when your user space is done, this file system will be destroyed. But if you create a file system on disk, then and you write to the disk, that you can expect guarantees of persistency at least. Perfect examples demonstrating the software nature of file systems probably could be some already existing virtual file systems that we have in Linux, such as tmpfs, ramfs, the prots directory in your Linux, sys, dev, all those things looking like files but not being files. Those are just APIs into the kernel, or tmpfs and ramfs. They allow you to create files and folders on top of your RAM, not stored on any disk, so on restart it will all be lost. But those are still real file systems. You can still create folders and files and sockets and everything in them, and this will be all working. So for the kernel, actually, it doesn't matter too much, I would say, where your stuff is stored in in user space, virtual memory pages, or physically in RAM somewhere, or on disk or whatever. The file system itself doesn't care where its bytes are going to be stored. Disks and file systems are very much related, but they do not depend on each other too much. A great example demonstrating the software nature again is file system Fuse. It's called file system in user space. This is the abbreviation for Fuse. And this is actually a kernel module implemented at least in Linux, BSD, and Mac. And it allows you to create file systems directly in user space. So you can, for instance, use system calls like open, read, write, and so on, stat, and their handling will happen in user space, not in the kernel. So the kernel will proxy all the stuff to user space implementation of a file system. This way you can create yourself any file system, which will look like actual files and folders, and other processes will be even able to access it. Here is how you might create it in the terminal, but you can also obviously use it in C and C++ code if you find a way. It's just, I mean, there are probably some libraries which allow you to do that easily. Personally, I didn't work with Fuse in code, but I did use it more than once for some convenient stuff. For instance, on this slide, I'm doing the following. I'm preparing a folder in which I will create this file system, like implemented actually in user space, not having any real local files. And then I create via Fuse a file system, which actually on every access to files and folders will go over network to another host. This is called SSHFS. So if you have SSH access to any server, for example, then you can, via SSHFS, mount remote folders on that server to your local computer and then use any sort of local software that works with local files. For instance, you could do it like store source code of some project on a remote server, build it there, compile, run tests remotely, but you also want to use some UI code editor like Sublime, VS Code, Visual Studio. With SSHFS, you could mount remote folder having source code from the server to your local computer and use your editor locally. And editor will see it as just local files, except that when it will do under the hood, deep somewhere, open, read, and write, it will actually, those will be proxied over the network via SSHFS program, implemented in user space. That's very cool stuff. You can see which file system your Linux kernel supports by printing the content of the prots file systems file. Those are file systems which are coming out of the box in Linux, as literally parts of the kernel, not some external drivers or modules, just literally compiled into the kernel and supported right away. All this information that we just learned means that there is something below file system that the latter uses to store data on external device or in memory. Because file system is software, devices are hardware. From what I'm saying, it sounds like they are barely connected, right? My question to you, try to think about it. What do you think is between file systems and hardware? What is doing the job of bringing the data back and forth between them? The commands. Put the video on pause, think, and I will reveal the answer right now. The drivers. The drivers are the thing which is connecting software world to the hardware world. So file system, when it is actually mapped on some hardware device like disk, it will somewhere down the call stack access a certain driver which will talk to specific device and send it very low level commands like this sequence of bytes write by this offset, this sequence of bytes write by this offset return me sequence of bytes. Those will be the kinds of commands that the driver will be executing, and those sequence of bytes will actually be like packages of data that file system wants to write or to read. To create a file, to delete a file, to write data into file. There are three types of storage devices: char device, block device, and network device. Char device, probably the easiest way to think about it, is just a device having sequential access. So you can go, for instance, forward, but you cannot go backward. It's like a stream of data. Data can be anything. It can be as simple as literally chars. Like when you press something on a keyboard, you produce chars, they get delivered to the kernel, like literally individual chars. And you can type new chars, but you cannot untype them, or the kernel cannot look what you typed like 10 minutes ago and go back to that in time to read what you wrote 10 minutes ago, unless it was saved somewhere in user space, but on device level it's not supported. So keyboard is actually a sequential device, char device. Another example could be your monitor. Monitor is displaying pictures at a very high frequency, but it's basically static pictures. You cannot go back in time and see what sequence of pictures the monitor was showing like an hour ago. And again, unless you are recording it, but the device itself, the monitor, doesn't allow that. It's sequentially throwing you a stream of images. Or a printer. Printer can also, we can say, it's a char device because it's printing paper, but it cannot unprint paper. You cannot reprint some papers that it was actually printing some like a day ago. Right, again, unless you do something on top of it, but the printer itself is unable to do that. That's why it's a sequential device. And the char is a paper. Block device is something that allows you arbitrary access. So you can just read any part of the device. You can read it in any sequence. You can always access any byte on the device. I would probably characterize it like this. It's also means that it's probably having limited size. On a keyboard, you probably can type potentially unlimited number of chars. On printer, you can print potentially unlimited number of paper sheets, but on disks, on block devices, you usually have limited number of bytes. You cannot infinitely expand them. And to this, we will put the traditional devices like SSD and HDD. But also an interesting way to think about it is that a book is also a block device. You can open any page, you can reread it, it's limited in size, you can go forward, you can go back, so technically book is a block device. Normally, I don't think it's common literature to separate those other devices into separate category, but I do it nonetheless, the network devices, because even though they look like sequential devices, meaning that they basically stream bytes on your computer or frames, their logic is so much different and complicated when you deep slightly digger than into just char device and block devices that I prefer to put them into separate category. And about this stuff, network, we will talk on a separate lecture more. Today we concentrate on the block devices. And I wanted to start with the HDDs or hard disk drive. We will look into internals of HDD and SSD because most of the software that is working with persistent data will work with HDD and SSD. And it does make sense for you to know the trade-offs between them, especially if one day you grow to be an architect of whatever, like cloud. In clouds, you can quite often choose what do you want to have, HDD or SSD, or they sometimes can call it hot storage and cold storage. And they have different pricing, different characteristics, different speed of reading and writing. And depending on your task, you ideally should be able to choose which one is more appropriate for your specific case. So I hope the material I will show you next is going to be helpful. We will start with HDD because it's just simpler in how it's organized. And HDD is a device which consists of controller, magnetic disks and reading heads, which you can see on the pictures. Basically nothing changes over decades in this besides some small fine-tuning things, and otherwise this HDD is pretty much very stable in its design. And the controller is a small computer which will control the head positions of those like reading heads. It will manage the read-write operations, receive them as commands from the CPU, and will communicate with the processor using interrupts, that we saw on the previous lectures. Magnetic disks are made of cheap material such as glass or plastic, coated with other material that interacts with magnetic fields and can store bits. Long time ago this material was steel oxide, red powder, so the disks were looking like a little bit rusty, like on the picture, and then cobalt-based alloys started being used. The disk is covered on both sides with this material, and how to store bits on it. For that, we need to look closer. Let's do that. If we look under microscope on the surface of this disk, we will see a structure like this. We will see that it's not actually as smooth as it looks for human eye. It's not just continuous atoms of metal or whatever. Actually, it consists of small segments which we could call magnetic domains. Those small cells. Each magnetic domain is a piece of material where magnetic moment of the electrons is pointing into one direction, and in different domains they can point in different directions. We could, if we go even closer and schematic, then we could imagine it like this. This is the surface, and we have some domains pointing, let's say, up, and some domains pointing down, and we could say that one is 0 and the other one is 1. And then we could store data. Now we just need to figure out how to change this direction to overwrite 1 with 0 and 0 with 1. So we could write data, and then we need to figure out how to read it. This is how it works. For that we need those reading heads which are gliding over the disk. When we need to write something, the reading head will get positioned by the controller on top of the domain that needs to be written, and then it generates magnetic field, which will change the direction of the electrons in the domain. So this way it can override 0 with 1 or back. And for reading, the head will get positioned on top of the domain and it will read the magnetic field of those electrons. It will not override it, it will just read it. And then the signal will be delivered to the controller and it will understand what was the direction up or down, and hence 0 or 1. The disks are spinning at crazy speed of 250 rotations per second easy. Heads will glide above the disks and write and read magnetic fields. You can imagine that the scale of that is going to be very, very, very small, because each magnetic domain is like ones or tens of nanometers, which means to read like individual domains and to write them, the gliding head has to be above the surface approximately on the same distance of several nanometers. And right now, the distance between the reading head and the surface of the disk is going to be approximately like 3 nanometers, is completely normal. The next question then is that since we figured out how to store individual domains and to read them, how are individual bytes in these devices are addressed? Because it's not just an array of bytes, right? It's multiple disks, multiple floors, and on them the data is stored in circles, because when you position the reading head on top of the disk and disk is rotating, if the head is not moving, then you have a circle which will go under the reading head. We need to find a way to address this 3D structure as actually an array of bytes. There is a common terminology used for that, a common way of addressing, which is called CHS, cylinder, head, and sector. Cylinder is called the ring. Why is it called a cylinder, even though it's actually a ring? I think the idea is that when you have many disks on top of each other, and you have the same ring on each of them, then together they like form a cylinder. Probably that's the logic, but for me it's somehow counterintuitive. The next would be head. It's basically means which floor you are going to be reading, because for every floor you will have different reading heads. And the sector is going to be literally a sector on those circles. By those three numbers you can select segment of bytes on the disks. It also means that you cannot really address individual bytes, because this is mechanical work. Those disks are rotating very, very fast, and this reading head cannot possibly address every individual magnetic domain. So to make it more efficient, the heads have to work in bulk, and they are only able to read and write data in segments, like in the individual sectors, which usually are supposed to be about 512 bytes. So even when you write 1 byte to a disk or read 1 byte, this will actually trigger potentially reading or writing of 512 bytes at least as a whole block. Simply because access by individual bytes is simply not technically feasible to do. It would be super inefficient. And this naming of addressing cylinder head sector, well, you can see there is no byte in this address, right? There is sector is the smallest thing you can possibly address on HDDs. And the naming for me was a bit confusing, so I invented my own floor ring segment. That at least sounds to me more natural. I don't know about you, but yeah, this helped me to understand a bit better. Those disks, they do have this weird 3D addressing, but it would be strange for the kernel to care about that, right? Because think about it. Imagine that you have HDDs with this way of addressing. You have SSDs probably with another way of addressing. You have flash drives with another way of addressing. You have maybe some whatever other devices with their own way of addressing, right? We need some common way to address all devices the same, which would be very convenient if we could represent every device as just an array of bytes, not segment, cylinder, head, sector. This is inconvenient, and this doesn't scale to different devices which don't even have such concepts. So The kernel instead, it operates on like linear address. So it literally represents every device as a byte array. Then it's job of the controller or of the driver to translate this linear address into addressing of the specific device. Because it's not too hard to invent a formula where you can transform 3D address into linear address. If we would just find a way to put all those segments one after another, this would turn into an array of bytes, right? We would just need a formula to understand from one number how to split it into 3 numbers, and there is this formula. You can see it on slide, you don't have to memorize it, but I just wanted to show you that it's not too hard. And this way of addressing is called logical block addressing, so it's just logical addressing of a device as a sequence of bytes, an array of bytes. And then this LBA address can be transformed into any sort of CHS address, which is going to be also, by the way, different for different disks, because some disks will have different number of the, like literally surfaces of the heads. Because this translation will be heavily depending on every specific device, but the kernel will not care. The kernel will give this job of translation to drivers and controllers. What about performance of HDDs? Well, performance is actually not bad. It's still fine to use HDDs for very many tasks, with some rare exceptions, I would say. Because no matter what disk you use, if you do depend on it, like if you really read and write it very often, your program will be slow. It doesn't matter what you use. HDD, SSD, it makes not a big difference, to be honest. It's not very many tasks where HDD is not as fast enough and SSD is fast enough. I would say if such tasks exist, sometimes, yeah, okay, it's justified, and those are few cases, and in some other cases it might mean just bad design, probably. And HDDs these days they operate approximately at the following speeds. The disks are rotating constantly, so the reading heads could access them. And on the servers, they're going to be rotating like 15,000 times per minute approximately. On home computers, it's going to be a little bit less, between 7 and 10,000, simply because home computers usually don't experience such load as servers do, which means, by the way, if we calculate it into how much time does it take for a disk to rotate once. It means more than 4 milliseconds for one rotation, or 2 milliseconds on average to access any segment on the disk. So this means if you are going to read the disk often and you are going to read new data often, which is not cached, then yeah, you will have quite a large latency. Even network doesn't always have this kind of latency, so it's very slow, mostly because it's mechanical, so it's not electrical. You depend on mechanics of the rotating disks, which is obviously going to be thousands, millions of times slower than the speed of the CPU, which works with electricity and speed of light. But you can kind of make it not so bad in your task. If you do have to read or write the disk, there are ways how not to pay so much for every single write or read that you do. And one of the most common ways is just make all your operations, or as much as you can of them, sequential. Because in case of HDD, it's very clear why does it make sense. If you read bytes non-sequentially, like you read, I don't know, from right to left, then you will have to rotate and read, read next, rotate, read next, rotate, read next. So every read will cost you one rotation to wait for. But if you find a way to reorganize your reads or writes in a way that you read a bunch of data in a row or write a large blob of data in a row, not in different random places, then you might do it in one rotation. Then you will pay, like, imagine you wanted to write 100 records of whatever. You could merge them into a single buffer and make one write. Or for reading, you wanted to read many different pieces of data close to each other in one file. You could instead maybe read more data, but in one go, and then extract those pieces of data from the consumed buffer, and then you did one read, or like one write, and you pay once those 2 milliseconds. This might actually be very, very beneficial. And this hack about doing your access to devices sequential, it works not only with HDDs, it works with literally every device and even with the main memory, as we saw it on the previous lectures about memory. How it's beneficial when you pack your data more tight and then it fits better into the CPU cache and then you save on not going into the main memory too often. Here the logic is the same. Those disks are mechanical, so therefore they can fail quite easily. Because mechanical elements, when they are moving, they eventually get worn out, they break, they need maintenance. Strong enough blow on the disk can cause, for instance, the head to touch the surface and then it will scratch the surface and then all your magnetic domains are gone. The same can be caused by particles penetrating the disk box. If they, like some dust gets down on the surface of the disk, you're also probably gone. The data will be damaged. It also is believed that HDDs are very vulnerable to magnets, as they record data via interaction of magnetic fields, but actually it's hardly possible to damage a device, an HDD with a magnet, because like in order to remove data from a disk with a magnet, you will need magnet of such strong power that it will remove the iron from your blood before it removes data from the disk. That's how powerful magnet should be in order to damage an HDD. But even with perfect maintenance, temperature, like no crashing or shaking or anything in data centers, HDDs don't live too long. They get replaced every day, many of them. They serve like several years on average and then they need to be replaced because of how much load they experience in the data centers. A popular alternative to HDD is SSD, solid state drive. It doesn't have any mechanical parts that move at all. Only current and electrons move in this device. Nothing is rotating, nothing is moving. And SSD memory has nothing to do with magnetic fields this time. So it's also harder to break it with any sort of magnetic stuff, and it also is more resistant to any sort of shaking or or like physical damage, because there is nothing to break inside, unless of course it will like split somehow open. But otherwise it's much more stable than HDDs. That's why it's also relatively popular in Internet of Things, in embedded devices, which need to be moving, because then they're just more robust and it will live longer. And SSD, even though it looks outside very similar to HDD, although these days it's much thinner usually, it consists of a controller and memory blocks. Controller, same as was with HDD, which needs to receive commands from the CPU and send interrupts back. And memory blocks instead of the disks. And SSD memory is a special type of flash memory. It will store every bit or even a set of bits in an isolated cell. Completely unlike magnetic domains in HDDs. It's a totally different way of building memory. An SSD memory cell is actually a specially designed transistor. The device is quite difficult to explain and understand, maybe because I'm not very good with physics. But I will try. I will try to explain it to an extent to which I was able to understand it on a simple enough level. So let's look at this cell. It consists of several parts. First is a block of dielectric, so current cannot go through that material. Inside of this block is completely inside, like fully isolated from the outside environment, is a conductor. Current can go through the conductor. And we could say that if the current electrons, so to say, they would enter this conductor, they will not be able to escape from it without external help, because electrons cannot go through the electric. Not so easily, at least. So if you find a way to get some electrons inside this thing, then they will stay there until we remove them from there manually. And we could say then, this cell, whatever we are going to design it, how, we could say that if there are electrons inside, it's like 1. If there are no electrons inside, it could be 0. Or vice versa. We just need to find a way now to put electrons inside and then find if they're inside and then find a way to remove them. Just those 3 operations we need. let's start with the operation how to get them inside in the first place. So we will place this dielectric box on the platform, which is also made of dielectric. And we will have 3 contacts, one above, one on the left, one on the right. And we will do the following. We will apply negative charge on the left, positive charge on the right. Which means electrons will start flowing. They come here and they are wondering, like, where do we go? But they cannot go anywhere from here because this gray box on the left is not touching any conductor on the right. It's completely surrounded by the electric, so they cannot go. They cannot go from this small box anywhere. In theory, those electrons, they want to go here, right? Because they want to go to the positive charge. They cannot because there is a lot of dielectric between those two platforms. And we can help them. We can give them a hint. We can apply also positive charge on top, and then electrons, they want to go like this. Because they sense both of those positive charges. And if we do it like this, the electrons with our little hint on the top will notice that there is a bridge. They will jump on that bridge. If the charge is strong enough, they will be able to do it even through the dielectric. They will start flowing, and then they will go to the other side. This effect is called quantum tunneling. It's when those electrons, they are not like little balls, really, it's just how I'm drawing them. But actually electron is like, you can imagine it's a function or it's a field. And if you make this field, like you can say big enough, then eventually it will, when we give it a hint on the top, this field will become more like this, into this direction, and it will almost teleport into this area. It's not really teleport, it's just this electron, it's not a ball which can teleport, it's not an object. But this function, like this cloud of this field, it can flow into this conductor in the middle when we give it a hint. And then suddenly we can just shut everything off, and some electrons which didn't have enough time to leave, they will get trapped inside. Now they cannot go anywhere, because there is no charge anywhere, they don't know where they could go, they cannot do this tunneling thing again. They will just stay inside. We just performed the write, so we put some electrons inside this thing. We changed it from 0 to 1, or from 1 to 0. It doesn't matter what we call 0 or 1, but we changed the state of the thing. And those things, they are called, this top is called control gate. The contact on the left is source, contact on the right is drain. Drain is where electrons are like being removed from. When the current existed, we saw that electrons were going from the left to the right and were draining on the right. And this thing in the middle, it's called floating gate, so it's floating inside the electric. This actually very much looks similar to how it's in reality. There is a microscopic photo of one bit which has all those things that we just saw. This platform is a floating gate. This thing here is source, this is drain, this is control gate. This floating gate is trapped inside thick dielectric layer, where electricity cannot go. Now my question to you, try to think in those simple terms. We have here electrons, so we changed the state, but we need to be able to change it back, because it would be strange if we can just write only once. Right, this would be like read-only memory of some sort. We need to find a way to evict the electrons, so they would leave from here, and we could change the state of the thing back. Put the video on pause, think, and I will reveal the answer right now. The answer basically is something that we could remember from school physics. It's that charges of the same sign, they push each other from each other. To evict those electrons, we could apply negative charge somewhere, for example, on the top. And then they would be pushed down by this large negative charge and will escape through source or through the drain. Could look like this. We just apply on top negative. On the right, we apply positive to give them a hint where to go. And then the electrons will again, with quantum tunneling, teleport, like jump over into the drain contact, and then they will leave. Now we found a way to put electrons inside and remove them from the inside. Now we need one last thing, how to detect if they are inside. This would be our reading operation. This is something quite untrivial, which to be honest I'm not even sure I completely understand myself, but I think I can explain it on a simple enough level. This is how it's working. We apply negative charge on the left. We apply positive charge on the top and small positive charge on the right. What will happen is that if there are electrons inside, this system together will look like zero from this point of view. Like if we would measure magnetic field from the source contact, we will see that it's not there, there is nothing. Because those negative electrons and positive charge on top, they will together become zero when we look at it from the outside. But if there are no electrons inside, then from the source, when we apply those charges, this system will look positive to us. If we can detect that on the source, we should be able to read if electrons are inside. One last untrivial question is why do we need also positive charge on the drain? This one. The point is, if we would not have it and there are electrons here, then current will not be flowing when we apply negative charge on the left. But it will also not be flowing even if there are no electrons inside. Because if electrons come here and then they get trapped inside, they don't know about this gate because they don't see positive charge here. Current will not be flowing in both cases. Then on the right, on the drain, we will not be able to understand if the electrons are inside or not. To understand it, we need the flow, the current to flow in one case and not flow in another. And for that, we apply here a small positive charge. If there are electrons inside, there will be no current. Because from this point of view, from the point of view of the source, everything on the right has zero charge, because those electrons will together with those pluses become zero. Electrons will simply stay here and not flow. But if there are no electrons inside, imagine they are empty, then the situation looks almost like writing. So electrons will come here, sense positive charge on the right, go here, the current will flow, and then it will flow here. So if the current goes out of the drain, it means there were no electrons inside. If it doesn't go, it means there were electrons inside. This way we can detect if this cell has value, has electrons inside. SSDs, similar to HDDs, they also have limited lifetime. Because of how this, how much they experience the current and the voltage and all those magnetic fields, eventually this will be damaging for the oxide, for the dielectric, on the atomic level. Like it will literally degrade over time. Like any material basically, it doesn't even have to be an atomic level, it's just on atomic level, it will probably happen faster and more noticeable, but eventually every material is degrading, and those cells eventually will, those dielectric things, they will also degrade over time. Which means, after a while, the charge might simply start leaking from SSD cells. The electrons eventually will start escaping, they will get trapped inside the dielectric in some holes, and at some point the SSD cells, the flash cells, they might be simply unable to hold the charge. The lifetime, like SSDs when they are manufactured, usually it's known relatively precise in advance how many writes they can do in total, like some millions of writes or whatever. After that, the data might get corrupted, and I think some SSDs can even detect that and slowly mark some segments of their memory as unusable if it degrades over time. And those memory cells, the flash cells, they get joined in huge arrays, which are joined into pages. And pages are merged into blocks. And reading on an SSD, also similar to HDD, can only be done by pages. On HDD it was by sectors of size approximately 512 bytes. On SSDs it's done in pages approximately the same size, something between 512 and 4 kilobytes. And this is necessary because you can probably in some way find how you could address individual bytes or even individual bits. But from the point of view of energy efficiency and engineering complexity, it doesn't probably make much sense. That's why it's easier to implement the writing and reading in a way when you can read or write multiple bytes at once, like pages. And in SSDs, it is done in the same way. So also, when you have an SSD and you write a single byte somewhere, you will firstly have some overhead on top, like due to the file system, because it will have to send a command to the disk to update the file size, update some metadata of the file, of the folder, and then also the data. But still, even if the device receives less than 512 bytes, it will write at least 512 bytes or whatever is the page size when the command finally reaches the disk. Also, physical internals of SSDs make the writing, deleting, or updating the data not very obvious how it's working. Again, for the purpose of efficiency, of engineering and electrical efficiency, I mean. The data on SSDs cannot be written in place, cannot be updated in place. On HDDs, I don't think that problem exists, but on SSDs, it's a real thing that once you wrote a memory block, like a page, you cannot update it. So it basically becomes read-only. But the memory pages, they are joined into memory blocks, which you can completely reset and then reuse individual pages from them. That's just how specifics of how it's done in SSDs, specifics of implementation which they have to live with. And here an example how it's working when we're working with SSDs. Imagine we have two memory blocks, X and Y. Y is empty and X has data like pages A, B, C. They are filled with something and everything else is free. Now imagine I want to write new pages, E, F, G, H. They get written, E, F, G, H, and I also want to update A, B, C, D. I cannot update them in place, so I have to copy A into a new page, already updated. Same with B, same with C, same with D. And the old locations of those pages, they become unusable. They become garbage pages. They cannot be used for anything. And then eventually we see that this whole memory block is full now. We cannot write any new pages in it. We need to free space, and for that the SSD will do the following. It will copy all the valid pages into a new block and completely reset the whole old block. That's what happened on the third picture. You see, we had block X, it was completely reset, and before that the data was brought over to another block. This number of writes that we do potentially for every logical write, number of physical writes here was firstly some data was written to A, then maybe it was unchanged during update and it was also copied here into A. Part of the A was updated, but probably not the whole A, right? Maybe some bytes remained unchanged, but we still needed to copy the whole page. And then again it was copied here. So we did like the same bytes potentially got written 3 times, even though we wrote them logically only once. This thing, when for one logical write you make multiple physical writes, is called write amplification. It's a property of SSDs and of some data structures like LSM3s, where, as I explained before, I think on this lecture, you write something into an LSM3, into its top level, eventually it gets, which is in memory, this one. Then eventually it gets dumped on disk, and then multiple times it will get dumped into lower and lower files, get merged, sorted with other files, and one piece of data might get written this way many, many times. Rewritten, rewritten, and so on. And this LSM3, it's supported by Tarantul in one of the engines that it has for tables, and in MySQL in the MyRocks engine. There is also a database called RocksDB. It also uses LSM. As you can see, SSD is a very complicated thing. In terms of logic, the controller here has to perform a lot of tasks. But an SSD, but it basically can be called a separate computer. Its controller should be much more complicated than for HDDs. Because not only it has to route your read and write operations to specific memory blocks in the device, but it also has to perform this garbage collection thing and block copying, removal of the pages, reset of the whole memory blocks. Right, there is like a lot of software in the SSD, which does a lot of work outside of the kernel, like just inside the device. Another job of the SSD controller is to keep in mind that SSD memory cells eventually get worn out, like they become unusable, as I explained. And SSDs actually try to balance your writes in a way that the cells of the whole device, they get used evenly over time. So it's not like in 1 year half of your device become unusable and the other half is like new. Instead, the SSD will try to make your device lives longer, but when it finally dies, probably most of its memory will already die at once. That's the idea, I think, of this balancing approach. Also, SSD, you can see that it needs to copy some data between different pages, different blocks. For that, it needs its own RAM. So it's literally like a small computer. It was just a couple of devices, but how can the kernel know in which format the data is stored on them? What file system is there? How to parse the bytes stored on those devices? When we plug in a flash drive or an external HDD or SSD, we almost never have to tell the kernel what file system is there. Usually, the kernel, the system, it understands it on its own. It just can magically read the files, right? Even though different devices might have different file systems, it still usually works completely flawless. My question is, how do you think the operating system, the kernel, how do they find which file system is on which device automatically? Think about it, put the video on pause. I will be revealing the answer right now. So my questions usually don't have complicated answers. In this case, it's also relatively simple. We could say that in the beginning of every storage device, let's store a special control block, which will have some standard structure the same for all file systems, regardless even of file systems at all. Could even be just hardware thing that all devices have to do this in order to be compatible with the modern computers. And in this initial control block, fixed size, they will store some metadata like name of the file system or ID of the file system or something similar to that. And then the kernel potentially could just read this control block by the 0 offset of the device, like first bytes of the device, represented as array of bytes, parse it and then understand what file system it is. And most likely will even be able to work with this file system if it's something that the kernel supports out of the box. And this thing actually exists. It's called MBR or Master Boot Record. For hard drives, it would be the first cylinder, first ring, first sector. For devices that work with linear addresses with LBA, this would be just the 0 address, like with SSDs. And conveniently, the size of master boot record is 512 bytes. So it's literally one sector on disk, one page on an SSD. And this master boot record thing, it will have the code that is launched by BIOS if the machine boots from this device. The code will not be too complicated because it's very limited in size. It's just mostly expected to do a jump into a real program like bootloader. We saw it on the first lecture, I think. And there is also storage partitioning table. There are maximum 4 partitions at this layer. So at the top level, a device can only be split in 4 parts. Each partition will have its own record where it starts, where it ends on this device, like byte offset we could say, and what type partition it is. And then it can also be used already sometimes to detect a file system type on every specific partition. Partitions are obviously Optional, by the way. You could have like one partition having the entire disk, and other partitions could be empty. It doesn't always have to be 4. And each of those 4 partitions can be final, like actual file system already there, having user files, operating system, and everything else, or it can be a nested partition. So it can have sub-partitions. For instance, there is a partition type called GUID partition table, or GPT, and there might be many sub-partitions in it, more than 4. On the top level, as I said, you can have 4 partitions, but below that, sub-partitions can be many more. And every partition will have this record where it says the start and end, partition type, file system header, optional, and so on. The header of every partition will contain information related to its type. If it's a final partition containing data, then what file system there is, file system header, bootloader at the beginning, which can already launch the operating system stored on this partition, if there is anything stored at all. And the header of the file system will have some magic identifiers by which the kernel can identify what file system it is. This header of the file system is called superblock. For me, it sounds a bit weird, but this is the terminology used in the source code and in the documentation and various literature. In the kernel, you can also literally find the definition of this superblock thing, of the header of this file systems, where you can see that for every file system, the kernel wants to know its block count, how many blocks are free, size of the block, various flags when it was mounted, and magic number. Magic number is what will be used to determine the type of the file system. And the types, the kernel will just check what number is matching, and then it will see what type it is. For instance, in Linux, I found those constants in the kernel that it supports RAMFS, TMPFS, X2, 3, and 4, even Minix. Minix, you remember, it's like the father of Linux. MS-DOS file system, NFS, probably more, I don't remember if I copy-pasted them all. It just looks at this number and then compares it with magic, understands that this file system is here or the other one is here, or it doesn't recognize the file system, then nothing will work. Let's take a look at a couple of examples of specific file systems, FAT and ext2. FAT, file allocation table. It's the simplest one, so we'll look at it first. The idea is the following, that entire storage, entire device, is divided into sectors, ranging in size from 512 bytes to several kilobytes. You can guess that it's probably the most efficient if one block of the file system will match one block size of the device which it is stored on. Each file will consist of a chain of sectors that can be located anywhere. A sector has just a link to the next one, which has a link to the next one, and this way you can read the entire file. And the last block will have a flag that it's the end of the file. So it's very simple. All the files just forward list of blocks, and you can easily create new files and extend existing ones. As long as you have 3 blocks, it will simply work perfectly. But there is a problem with that, with this organization of storage by design. The problem is that at first it will work fine. Like when your device was empty, you create new files, they will be okay because the blocks will be sequential for every file. But eventually, when files will grow in different random order, they will get deleted, created. You will have fragmentation issues, that files will be entangled with each other. You can still follow them like as lists of blocks. They are still correct. It's just to read one file, you will have to jump here, 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 or read this one like this, right? It's readable, but there is a problem with that. As I explained before, on HDDs, it's going to be very, very bad, because if the sequential reading of those blocks will actually require multiple spins of the magnetic disk, then you will read one file very, very long. It's going to be extremely slow. On SSD, probably it will not be too bad, but on HDD, FAT file system eventually will degrade very, very badly. Nonetheless, it's It's good as a teaching example because of how trivially simple this file system is. You can literally read it completely in the kernel. It's not too big, very understandable. I tried to bring here some code samples from the kernel on the slide. You can see that this kernel structure for a file chain, it has, like you see, specific hard-coded sizes of every field, which field, like type of the file or whatever, next block ID and so on. It takes a specific number of bytes, so it's encoded always the same way on disk. And this would be the kernel struct for the folder, which also has very specific sequence of fields of specific sizes, which later, exactly like that, get encoded into bytes stored on the disk. The next file system is ext2. It's called the extended file system, second version. And this is the second version of the family of extended file systems, which comes directly from Minix, the operating system created by Tannenbaum, from which Linux was started. Extended file system ext, it's quite poorly documented, to be honest. The first version is considered outdated, I guess. And ext2 is already quite readable and very much usable file system still to these days. Yeah, there are also numbers 3 and 4, but they are a little bit more complicated. So we are going to look at the second one as not too trivial, but also not overly complex for us to understand. The ext file systems, they are in a way like on a high level similar to FAT as well. Also working with blocks, I mean. But they have features like fragmentation awareness, so the files, they try to stay close to each other, the blocks of one file, they don't get scattered across different corners of the device. They are also good for flash memory because ext will try to reduce number of physical writes for how many logical writes you make. In ext2 file systems, all folders and files are described as inodes. It's a structure which will store attributes of a file or a folder like its name, permissions, different timestamps, subdirectories, list of blocks where data should be stored. And this is where the name for the inode term in Linux kernel is coming from. In Linux right now, I think it is used for every like file. It has inode ID or something, even though it not always is stored on ext file system, but it's just how in Linux it's operating now. It's using inode as a term for I think an entry of a file system. Although origin I think is here, yeah, in ext file systems. And the structure here actually is slightly reminding us of the page table from the how virtual pages get mapped to physical pages. It also looks a little bit like multi-level tree of fixed size. Just the size here is not exactly fixed, but the structure of the tree is similar. So here is how it's working. Every inode, being a folder or file, but usually like I guess a file, it can have up to 15 blocks. And those IDs of the blocks are literally stored just in that inode. See, an array of block addresses. Block address is like a block number. By block number, you can find specific block, like page on the device in which data is stored. And the first 12 block addresses, they contain physical addresses of physical blocks storing the data. Data which we put into file, like text, movie, or whatever, right? The last 3 addresses, they don't point at blocks with data. Instead, they point at the blocks storing addresses of other blocks. So it's like levels of indirection. The first one here, it points at a page, at a block, where we have multiple addresses pointing at the next blocks with data. So like it's those 12 addresses, they get continued here. This is the first block, this is the second, third, 12, this is 13, 14, 15, and so on. The number of addresses here depends on the block size, which is configurable for file systems. at least for ext. It's configurable, so depending on the size of one address and size of the block, there can be different number of addresses in this first level of indirection. When the file is growing, eventually it might exceed all those 12 and might exceed this first level of indirectness too, if it's a really big file. And then it needs more data. And then this is where the second indirectness level gets activated. Then this address gets filled with address of a block, which stores addresses of blocks, each of which is storing addresses of blocks which are pointing at data. So then the file's data is organized like this. Those are first blocks with data. Those are next blocks with data. This is pointing at the next blocks with data, next blocks with data, next, and so on. Eventually, if the file continues growing, then even second level might be not enough, and this is when the last one gets activated. The third, which will point at a block having addresses of blocks which have addresses of blocks which have addresses of blocks with data. And this is the maximum level of indirectness. It cannot go even deeper, but this already is enough to store quite large files. And this is all configurable usually. So if you know your use case, how big files you're going to have, how much data you are willing to spend on just the metadata of those blocks, then you can configure the page size to something more suitable to your case. But to be honest, I never saw anybody caring. Usually default is good enough. So for example, if you have a block of size 512 bytes and 4 bytes for one address, then one reference table, like one of such blocks, can have 128 pointers. Given this information, you can technically calculate already how large can be the maximum file, the biggest file in ext. Depending on block size, it can go to terabytes. If the block size is big enough, then for every level of indirectness, you will have more and more data available exponentially, I think, but you will then have less number of blocks. It's like a trade-off. You will either be able to create very many files, but not of too big size, or not too many files, but of very large sizes. You would have to choose this trade-off on your specific case. But usually, nobody cares. The default is good enough. The ext2 file system will divide the entire device into groups of blocks. Each group will contain a copy of the super block. So like you see, it's here, one per device, and also in every block, it will be like in the beginning stored a copy of this super block. It helps with fault tolerance, because if this is stored on HDD and HDD get damaged, then we can still restore some individual block groups. And then after copy of the super block, it will store metadata, block bitmask, inode bitmask, and inode table. And then some number of data blocks, which depends on the size of the device and on the size of the block. Data blocks is where the actual data is stored, the content of your files, the list of files of your folders, and so on. The inode table is where stored metadata of the files and folders. Like for every folder, for every file, you will have one entry in this inode table. Some entries in the inode table will be free, and they will be taken when you create a new file or a new folder. Then this cell gets taken. When you delete them, the cells get free. And then when you want to create a new file, you need to be able to quickly find a free cell in the inode table. And when you want to extend your file, like to write more data, you need to be able to quickly find a free block in this array of data blocks. For that, there are bitmasks. It has as many bits as we have data blocks, and inode bitmasks. A bitmask has as many bits as cells in the inode table. And when you want to find a free block for new data, for example, then you will just quickly find in this bitmask whatever bit is 0, and this index of that block, of this bit, will be also number of the free data block. Then you can do it fast. And inode bitmask also, you just want to create a new file or a new folder, then you find here a free bit, And then you can quickly find the entry in inode table, which is also free, and then you can take it for your new file. This is how it's working. So the bit mask scanning is going to be fast because it's going to be packed into very small number of pages of the device. In theory, like let's imagine we remove those bit masks. Stuff will work. You can still in linear time just walk this whole table, find free entry. When you want a new data block to add to your file, you can also walk linearly all those data blocks. The problem is that it's going to be slow. You will need to make many more physical reads to find some free cells here or free blocks here than you would do if you were just reading those bit masks. Bit masks will be much smaller. And those you can even probably keep in memory. My bet would be that perhaps the kernel is keeping them in some sort of cache for fast access, so it doesn't even have to read them all the time. Let's see some examples of the code about ext2 file system from the kernel. It's actually very simple. You might be able to just also open it and read. It's not complicated. And we can find here this inode, which has firstly some metadata. Like you can see flags, probably file or folder size, user ID. Maybe this is creation time, number of blocks, how many times it's kept open, and like soft and hard links at that inode instance. And then we can see here the block numbers with data. You can see it is 15, like I was explaining before. 12 for direct access and 3 more for indirect access when it gets too big. We can also see here the addresses of the bit masks. Those are not bit masks themselves. It's not just 32 bits, that's not enough. This is actually address of the block where the bit mask for the free blocks, like the bit masks of the blocks, is stored. This is address of the block where bit masks of the inode is stored, inode table. And this is actual block where the inode table itself is stored. And what is coming after that is already the data blocks. And you can also see some constants here. Minimal block size in ext2 is 1 kilobyte, maximum 4 kilobytes. Then number of direct blocks is 12. The number of the block having first level of indirectness is 12, if we count from 0. And then plus 1 is the second indirectness, and plus 1 is third indirectness. And this is total number of blocks, 15. As you can see, the memory can be allocated and structured in different ways depending on file system, how it decides to treat the blocks, to use which ones for metadata, which ones for data, and so on. That's a lot of file systems, by the way. They do it in different ways. All of them store everything in some special way. And the kernel needs some mechanism to cope with all this variety. Like this is slightly similar to different standards for different things, doing roughly the same, storing data, but doing it in myriad of different ways. The kernel cannot possibly have myriads of different implementations of the complete stack of the file handling. Obviously, down somewhere close to the driver, the implementations are going to be different for different file systems, but most of the file operations, they don't normally care what file system they are targeting, right? When we open files, read and write them in code, we usually don't care what file system it is, really, right? We just want to use files, store data in them and read the data. To cope with this variety of different file systems working in different ways, the kernel introduces a concept of virtual file system. It's an interface. So the kernel says that whatever file system wants to be compatible with me, the Linux kernel, has to provide me an interface with which I can interact with this specific file system. And how this interface is going to be implemented for any specific file system, the kernel doesn't care. It just wants the file system to give it an interface. In terms of C++, we could imagine it's literally a pure virtual class with many virtual methods, and every file system has to inherit it, override and implement all the methods, and then give an instance of that class to the kernel. as a parent pointer. Or in Java, all the methods are virtual, I guess, or in C. Since the kernel is implemented in C, it cannot do it so simple. Instead, in C, the interface is looking like a struct, which has many members, and every member is just a pointer at a function. And when a file system wants to be supported by the kernel, it has to create its own instance of this super operations thing, fill in all the function pointers to point at specific implementations of specific operations of that file system, and then give instance of super operations to the kernel. And then kernel will call those functions by pointers. And everything that is above those operations will be the same for all file systems, shared code. It's just only when the kernel finally reaches invocation of one of those methods, it will already branch out into different file systems, but already at a very low level, so not much code is going to be duplicated. It's very easy to maintain this way. Schematically, it could look like this. Imagine that we write something into a file by the given file descriptor. We want to write this buffer of this size, and we make a system call write. It enters the kernel, where it will find the file, struct file, by the given descriptor, where it will invoke the method write of that file, which will invoke inode, write inode of that file, because this not necessarily is a file, right? It could be a console, could be socket, could be a pipe, right? But if it's a file, we will eventually reach a place where we'll call inode, write inode, and then it will branch out, because this will be already a virtual call, which for different file systems will be implemented differently. And then in the end, those specific file systems add some metadata, use some caching or whatever, and will give to the device, to the driver, a very specific simple command like write this number of bytes there or this number of bytes there. And this will already be done without depending on what file system is asking for this. So the whole variety of file systems, it gets isolated at this level, and everything else is shared, which is very convenient, very good design. Inode, it's not only existing in kernel, it also exists in some way in user space. You can find it through the structure dir end and through the call stat or fstat or similar system calls to find metadata of certain files or folders. They will have this either dinode or whatever other field resembling this inode name, where you will see the number of the inode. It's not very usable, to be honest, in user space, because what are you going to do with this number? It's not very useful for anything, to be honest. But I think it can be used in some other kernel APIs, for instance, for watching the files to catch their changes. It might be used, for instance, if you have a backend server which is running as a daemon and you want to implement config reload without restarting the server. One way is that your server could read this file like every second to check changes. Another way is that in Linux at least, but I think also in Windows too, you can install a watcher or on specific file entries and block some thread and until it notices that the file was changed, and then it will wake your thread up. To be honest, I don't think I ever used it directly, but I saw it being used, so it might be a nice tool if you will remember this thing and eventually you face similar task. You can remember it and use. I don't remember how it's called. It's IOCTL or inode watch or something like this. Probably this is where this inode number is given then. So you could watch a specific inode, but I'm not sure, to be honest. I will not pretend that I know. And from that moment, the topic of file systems is finished. You can still dig into specifics of different file systems if you want. All the basics that we need, possibly we already have. Everything else is already becoming user space code where we usually do not care about file systems. What we do care in user space mostly is this entry, a file, or it's a directory, or it's a socket. Is it readable? Is it writable? Is its size? But those are not file-specific things, to be honest. Most file systems will have all that. And in user space, you can obtain it pretty easily with the system called stat, or fstat, or fdstat, or it has like many variations. But they all return the same thing, where you can, for every entry in your file system, see if it's a directory, if it's a regular file, if it's a symbolic link, you are allowed to read it, to write it, to execute it, and many other attributes. It's not everything on the slide. Here I launched it and I was trying to check data of my own executable file, metadata, and I see that it has this weird inode, 8.5 kilobytes, 24 blocks. Maybe it's a block number, I don't know why it's 24. Seems too big. It's a regular file which I can read, write, and execute, which I literally just did. And it shows that the creator of the file is 502 and my UID is 502. I can also look at a folder and I will see that it's a directory. I can also do with it various stuff. It has no blocks for some reason. I think I launched it on Mac, so here the meaning of the concept of blocks might be just different. As you saw before, this concept of blocks, of pages, it's very low-level stuff. I wouldn't, to be honest, rely too much on this number for anything. Even size, like it makes sense for normal files, but for folders it's already relatively pointless. Like, what does it say? 160 what? 160 files in this folder? No, probably it's metadata size of the folder. I can also run it with the source code file of my own program, also has some meaningful size, somehow a lot of blocks. The data gets written to or read from devices through drivers linked into the kernel in form of dynamic libraries or sometimes already embedded in there, implemented out of the box. And they just provide API for writing data. By this offset, write this buffer of this size, or by this offset, read me those bytes into this buffer. That's all the drivers do, basically, for storage devices. And the question is then, what would happen if there would be nothing else but file systems and then directly drivers? If the API, like read and write, would be called at every access to storage device. Like on every write, we need to make physical write to HDD. Imagine that. That would be very slow, especially for writes. And the access would be too random in terms of locality, because usually it's too difficult to organize sequential or delayed access manually for every program that is working in the system, especially if they touch the same device. Maybe even the same files, but usually at least the same device. Yeah, that would be extremely slow. Even for SSDs, it would also wear them out a lot, because SSDs have limited number of writes. And to make life easier for programmers, the kernel has IO operation scheduler. Tries to make the problem of slow storage devices not so severe and to wear them out not so fast. It's a little bit similar to the process scheduler, but IO scheduler works with each device separately and it organizes the requests instead of tasks. So we can imagine that every read and every write we do, they are requests to receive data or to put data on the device. And those requests we could execute in different orders, we could delay some, put some in different order in the queue, right, when they go to the same device. And in theory, even if from user space we receive completely random sequence of those commands, we could reorder them a little bit to at least make more writes sequential or more reads sequential, or merge some reads into one read. Right? For example, imagine we receive a couple of requests to read certain data from disk, from different, even for different files perhaps. We could, if we see that they are close, like maybe reading the same the neighbor blocks, or even data from one block of the device, one page. We could technically execute them as one physical operation and then split the result logically and return those two results to different operations. Then for two operations, we make one physical access. Or another example, we receive 4 write operations for the pages number 3, 1, 4, and 2. This would be approximately 3 disk rotations to perform those 4 writes. We could technically reorder them to make them sequential. So we write 1, 2, 3, 4. And then it could be done on HDD in one rotation of the disk. That would be approximately 3 times faster. And this doesn't even cost anything to do. It seems like a very simple operation, right? Just catch those 4 writes and execute them not right away, but wait until they get accumulated a little bit and then execute them as one. This would be very nice for HDD, for the storage device itself, to reduce its wearing out, and for us, because average access time is going to be faster for all of those operations. In Linux kernel, there are many schedulers doing those 2 operations of merge and sort. The first one we will look at, it's called Linus Elevator. It's called after Linus Torvalds and analogy with an elevator. Analogy is the following: those operations of reads and writes, you could imagine them, each of them, as somebody who wants to go on an elevator somewhere. Let's see, like we have a building with 20 floors, and on different floors people press the button of calling the elevator to go up or down in random order, like somebody pressed button on floor number 5, 15, 1, 20, 2, 7, 9, 4. Right, the elevator, what it will do, it will not go like in the order of the buttons being pressed up and down all the time, right? When an elevator goes up, it will pick people as soon as it passes one of the people who had the button pressed. In the order in which elevator is going, not in the order in which the buttons were pressed. This is very efficient for the elevator and faster for the people. And the analogy is the same here for the I/O operations. If user space wanted to execute number of random writes here, there, and in some other 4/5 places, we could in theory just reorganize them in a more efficient way, if the scheduler is able to detect that and to merge and sort them appropriately. And Linus Elevator is doing the following. Just 3 operations. It has a queue of requests coming to a specific device on which this scheduler is activated. And when a new request is coming, like new read or new write, it will firstly try to find an existing request accessing neighbor data. For instance, if we want to read bytes 5 to 10 and there is already operation accessing bytes 10, 15, we could technically merge them into one operation and execute as one physical operation. If this didn't work, so we did not find an adjacent request, we could try to find a place between requests, so at least it's sequential. For instance, we did not have adjacent, but we've had some request for bytes before and for bytes after. Then we could put it in the middle. And then these 3 operations could be executed as one rotation of the magnetic disk. And if this also didn't work, then the operation will be put in the end of the queue. And this queue is being served. One request got executed, then the next one, and so on. Or maybe it can send it in batches. I guess it depends on the specific device if it's able to do that. The problem, which probably some of you noticed here already fast, is that with this logic, this queue becomes a little bit unfair, because if some user space process constantly spams reading of data in certain area, then it will be able to inject its requests into the middle of the queue all the time, and then all the other older requests will be just starved. They will be unable to get executed. To fight this problem, the Linus Elevator has a simple feature. All of those 3 features, they stop working if there is a too old request in the queue. If there is too old request, then all the new requests will go to the end of the queue. Then it becomes kind of not too unfair. At least requests will be not able to starve forever. Let's summarize the Linus Elevator. It's simple, I would even say trivial, but it has no latency guarantees because requests can wait very long. Because there is almost no protection from new requests not coming always in front of you, besides this one last comment about waiting for too long for some super long timeout. And it does not prioritize reads and writes in different ways, and those are actually different operations, behaving in very different ways, even though both are just physical accesses to the disk. logically they are extremely different. For writes, we usually don't care when it's finished. When we do care, those are special applications, when we do have some special steps to guarantee that. But even in those applications, we usually don't wait for every write to finish the device. We just send it to the device and then eventually it gets written. We don't need to block the thread to wait for it. With reads, it's more complicated because the result of the read is almost always needed here and now. You cannot delay receiving the result of read. You need some bytes to be put into the buffer which you gave to the read. So you cannot leave until the read actually consumes data from the device. And even more, until this one read is executed, you usually do not start the next read. Because you have some buffer of limited size, for example, and you just try to reuse it, or you try to read sequentially, not in parallel. With writes, it's not so. You can throw multiple buffers to the disk, also maybe sequentially, but again, you don't need to wait until they get completed. Which means reads and writes need to be handled in special different ways. And some, like Linux Elevator, doesn't even care, seems to me. It just treats all the operations as just operations, which means it treats reads a little bit unfairly. They need to be more prioritized, but if it would prioritize them too much, then we would face a phenomenon called write starvation, like some other schedulers have. It's a phenomenon when you prioritize reads too much, like for example, when you receive a read, you always execute it even if you have older writes pending. This would cause eventually writes to never be executed if you always execute reads, or execute it too rarely, and this is called write starvation. When you write not enough, you always prioritize reads. And there is another scheduler which is trying to address those issues. It's called Deadline IO scheduler. It has 3 queues instead of one. One big queue for all requests, which works the same way as Linux Elevator. So it does merge, sort, and all of that. And all the read and write requests are put there. But also there are 2 more queues for reads and writes separately. And those are FIFO queues without merge. Requests always get added to the end of those queues. Read requests go to the end of the read queue, write requests go to the end of the write queue. And when write request appears, it gets assigned a deadline. And read requests also get a deadline, but a closer one. So for instance, write needs to be completed within, I don't know, 100 milliseconds and read in 5 milliseconds. I just made those numbers up, but something like probably of this order would be fair. And when read and write queues did not reach the deadline yet, like the front item in them didn't expire yet, the scheduler will serve requests from the first queue. Same as Elevator, because it's the most efficient way. If you don't have too much load coming to the disk, then you will work in the most efficient way. As few physical operations as possible. But if one of the deadline expires in one of the queues, then it will be served first and then removed from the merge sort queue, or served from here and then removed from here and merge sort queue. And naturally, given how we give the deadlines to reads and writes, reads will be executed with higher priority than writes. So the logic in pseudocode could be looking like this. We could have a have function like pick next, request to execute, and it checks what is available in read queue, in write queue, and if neither of them has expired, then we take next merge sort request. Or otherwise we pick the one which has the most expired deadline. Those things I just mentioned, they do not solve the problem of write starvation. From what I explained so far, it could be that we have, for instance, very many reads, and they all expire, like 1,000 reads expired almost simultaneously, and then they will get executed completely ignoring the writes. Even though the writes might also be expired, but still we would prefer the reads. So there is still a write starvation issue in this scheduler because it started prioritizing reads. I suggest you to think about how deadline scheduler is actually solving this issue, which I did not say how yet. But the solution should be simple, so put the video on pause, think about it. I will give you the answer right now. The deadline scheduler does the following. To not starve the writes too much, it will execute maximum 2 reads in a row. and then it will prefer the write. If both read and write are expired, then it will only do maximum 2 reads and then already write. Regardless of the deadlines, then it will try to fight the write starvation this way. Although I would not recommend to remember specifically the number 2, because it's probably something that might get changed in the future, but you can always check it in the source code. It's all open in the kernel anyway. From the deadline scheduler, another scheduler under the name of anticipatory, branched a long time ago, like an extension. It was working mostly exactly like deadline scheduler, except that for reads, if a read was expired on a deadline, this scheduler would wait idle for a few milliseconds without doing anything, hoping that a new read might appear for the next block. The point is that reads in threads usually for files look like this. We read them in portions. And if the scheduler is aware of that pattern, then these reads could technically get executed in a row relatively fast. So the thread will not be blocked for too long, having to wait for sequential reads. It would still go to the device apparently for every read in this case, but it would be predictably blocked not for too long between every sequential reads. But in the end, this scheduler was removed from the kernel because it was replaced by the next more powerful scheduler, CFQ, or completely fair queuing scheduler. It is very similar, by the way, to the completely fair scheduler for processes and CPUs for tasks, which we saw on the second lecture, I think. And in this scheduler, there are 2 queues for each process. It's not just global queues for a whole device. It's for every task. There is a separate queues. And in one queue per task, everything is stored in FIFO order with deadlines, similar to deadline, but it's one queue. In the other, everything is merged as tight as possible, so merge sort queue. And the scheduler goes in a circle for all the processes, allocating a quantum of time for every task, for every process to work with the device. It will cover the anticipatory scheduler functionality because the process can also wait for new reads while using its time quantum. So inside time quantum, one task can do multiple reads. It also will collect statistics and it will also know how not to wait for new reads when it's not necessary. For example, when an SSD is used, the order of reads probably is not going to be as important as in HDD. But still, the time slices had, they were fixed in time. Its name is similar to completely fair scheduler for tasks, but the behavior is not exactly the same. Because time slices in the completely fair scheduler, if you remember, they were not binding, not obligatory. A task could in theory use more or less of its time slice. In this case it was not so. And to fix that, there is the last scheduler called budget fair queuing, even closer to completely fair scheduler of tasks. And this one actually allows to make the time slices more flexible, so to say, and it has weights and priorities. So more prioritized tasks will get more time to work with the device and execute their operations. And there is another scheduler called NoOp. It's the simplest one. It's even simpler than Linux Elevator because it only does merge. It has no sorting, no fairness, no deadlines, absolutely nothing. And this NoOp scheduler is only 200 lines long in implementation in the kernel. For comparison, the completely fair queuing scheduler is 5000 lines long. The task scheduler, for example, I think is 1 in the kernel. You cannot choose it from what I remember. But the IO scheduler you can choose per device. So many schedulers that I mentioned today, they are actually all present in the kernel together and you can choose. And by default, last time I checked was used CFQ. But probably by the time I'm reading this already, budget fair queuing is also available. And you can set it for every device different scheduler if you want. One question maybe is, why would anybody use NOP scheduler if there is CFQ or BFQ? The reason is that NOP has very low overhead computational. So if you have some low energy device, which writes something very rarely to some small flash memory block, persistent one, and doesn't even have much load. It just wants to save power and live as long as it can possibly on single battery. Then no, scheduler could be actually okay. It's just less CPU ticks to spend on evaluating how to execute it. So it could be a good choice for such simple cases. Even a scheduler doesn't really help to read data faster than the device allows that. No matter how good your scheduler is, if it works on an HDD, then to read anything you will spend milliseconds potentially. How would you speed the access up even more? There are ways. We can make stuff much faster and not even depend on specific storage device. Try to think about it, put the video on pause, and I reveal the answer now. Add cache. Add one more layer of the cache. Actually quite logical, right? If you read the same data over and over again, like you, for instance, execute the same executable file many times, then in theory you could just load it into memory once and then read it from memory, right? Why would you need to read it from disk and again and again? This would be good for disk, this would be fast for user space, also good, right? For writes also, since we don't even need to wait until the write usually ends up on the disk, we could also put the writes into some sort of in-memory cache and then flash it sometimes. Maybe some of the writes we would even completely able to skip if certain data gets rewritten multiple times, and only then in the end we would flash it to disk. Would be convenient, right? The kernel actually does have it. It's called page cache. It's the cache for pages for each device. It's a large tree which will store pages ordered by offset from the device, zero address, and when something we want to read, we will firstly try to look it up in the cache. And if it's there, then we will return it, otherwise we will have to go to the disk through this IO scheduler, driver and everything, then the result will be stored in the cache and then we read it. And the cache is just stored in RAM. It's a completely kernel concept, software. It has nothing to do with the device or with the CPU or anything. It's just a kernel module called page cache. And then the cost of reading and writing something like writing will be always fast. We will just always put it in the cache, not going to the disk at all. And for reads, when we read something that was already in the cache, it will cost us as much as just reading an in-memory buffer, which will be nanoseconds, maybe some like ones of microseconds because of the overheads of a system call in general. But it's going to be nowhere near milliseconds like with HDD. And there are different policies for writes. One is no write, so we could invalidate the cache and write on disk right now. Write back, it's like you write into the cache, and then eventually we will write it to the disk when it gets evicted from the cache or by timeout or whatever. And write through could be that we write to the cache and to the disk. And usually is used write back. It's just the default. You can though regulate it. I think you can also, when you open a file, you can specify a flag or direct, and then it will write without the cache and read. You can also use fsync to flush the caches to the device. But those are relatively complicated, extremely low-level things which you would have to double-check on your own if you ever decide that you need to absolutely guarantee physical writes. But it's good to know that it's possible and that by default you don't have that guarantee. It's very important to understand. Even that is not the end of the endless chain of schedulers, buffers, and caches. The user space also tries to help us somehow. For this purpose, some library functions, standard library, they perform buffered output. Not all of them, but some of them do. That is, they will keep the data in their local buffer until they get more data. Usually this means that like functions like printf, they might buffer data until they receive a new line character. Or they just might buffer data by, I don't know, by size or something like this. Technically nothing prevents them from doing that, and sometimes it's quite observable. This is all for today. Let's summarize what we have learned. Firstly, file systems provide access by file and directory names. They define storage format, literally how to organize the bytes, allowed operations, and their structure might be optimized for specific devices. Different file systems might be suitable for different physical layout, physical implementation of the storage devices. HDD disks are generally very slow, but also very cheap, and sequential access is much faster than a random access. It's going to be milliseconds for every physical travel to the disk and back. SSDs are going to be much faster but costly, more expensive, and random access is fast, but sequential is still faster. Sequential access is faster to everything, to every device, even to main memory. Sequential access is always good. Try to optimize for it. And SSDs will give us latency of like microseconds. Also, data is not flushed to disk right away. It will firstly go through IO schedulers, where it will spend a little bit of time until it reaches the disk. Page cache in the kernel is something that happens before schedulers. It will speed up writes for certain by just holding them in memory, and repetitive reads when you read the same data. Then it will be just consumed from the cache without using the disk. And now we're finally ready for the next homework related to what we learned today. You need to implement a file system. For this homework, you are given API similar to open, close, read and write. It's already there by this link. In the header file, all the documentation is available, and in the source code, in the C file, CPP, you will have to implement those functions which have missing bodies. And the file system is going to be simple. It's going to be just in memory, nothing on disk, no folders, just files. And it's going to be similar to the fat file system in a way that the files you will have to implement a sequence of blocks. And this is all for today. Thank you for your attention. Next time we will be looking at multi-threading, how threads are implemented, how to synchronize them, what are mutexes, atomic variables, lock-free, how this is all implemented at the hardware level in the kernel and in user space. Until next time.